Recording, and we're going to get through a little bit of L7 graphs of derivatives. It's a pretty big lesson, so that's why we won't get through the whole thing this lesson, so we'll just do part of it. Graphs of derivatives. So this is more just a little recap on some things you know. The derivative of a function can tell us a number of things about the graph. So this is more recap. If the derivative of a graph is 0, this means the point is a critical point. In the book, sometimes I call it a critical point. Yeah, that's it, yeah. Or sometimes, some books in Australia, we call it a stationary point.
Here we go in Australia.
So you're at minimum or maximum, doesn't matter. Minimum, maximum, or point of inflection. So our book spells it like this, X-I-O-N, inflection. So I'll just keep doing it that way. So that's if the first derivative. So by that I meant the first derivative of the graph. So if it's 0, it means that it's a critical point, i.e. a minimum, max, or point of inflection. If the second derivative is 0, this means that it is a point of inflection. So this is kind of just revisiting some things that we talked about. I'm concentrating. Oh yeah, by the way, like what I meant by this, I was just putting in symbols, you would say f dash dash x equals 0, just that pertains to that point. So if the second derivative is 0, so you could have written that instead if f dash dash x equals 0, just reminding you of the notation. So the next one here, if the second derivative is positive, think positive, it's like a smile.
Yes, it's a minimum.
So it's a minimum.
But it's confusing because you think positive will be max.
Yeah, you do. Positives at the top, don't you? Yeah. So think of it as more as instead like a smiling little.
Yeah.
Yeah, good point. So if the second derivative is positive, this tells us that the point is a minimum. And if you have trouble remembering that, try drawing it, and then that makes you see, hey, it's a minimum. Hey, so, oops. How you would write that as a in symbols with f dash dash x is greater than 0. So rather than them saying it as a sentence that the second derivative is positive, they might say f dash dash x is greater than 0. It's another way of saying that too. So just practicing out something. Same thing, if the second derivative is negative, it's a maximum. Notation f dash dash x is negative means that it's less than 0. So if it's less than 0, it's a maximum. I'll quickly calibrate it. Some of you might have noticed that if you happen to watch any of the last videos, the sound wasn't working, and that's because this headphone jack, someone had it in the mic jack instead. So instead of the headphone jack,
pal.
So now it's working again.
Darn it!
Alright, if the first derivative is positive, this tells us, of course, that the gradient. Yeah.
She don't even know.
So you don't know what it means. I was about to say that too. You know, it's been so long since you did it, or you forgot what you were meaning. So if the first derivative is positive, go away.
You press the X at the top, right, top, right.
Yeah. Okay, cool. So if the derivative is positive, this tells us that the gradient is positive. So the function must be increasing. Good, yeah.
Wait, if the derivative is positive, this tells us that the gradient is positive.
Yeah.
So the function
Must be increasing, like going from slowest to higher.
Why can you go back up?
Is negative.
Can we avoid a little side chat? Unless you're talking about math.
Yeah,
Okay. So if the derivative is negative, this means the gradient is negative, so the graph's decreasing. That's something that in graphs of derivatives, we talk about increasing and decreasing functions. So if it's increasing, the gradient's positive. If it's decreasing, the gradient's negative. Just to point out that little point there. So write down the intervals. By the intervals, I mean like the domain. Think about this thing like the domain. Write down the intervals over which the following functions are increasing or decreasing. So I've got to write one answer for where it's increasing and one set of answers for it's decreasing. Oh gosh.
Yeah, man, it is.
So sometimes it can help to graph it. Which part here, Bella, how would you explain where is it increasing?
Is it the ballot?
I'm not sure.
No, what do you think? Just a vague guess, or try to explain it in words as much as you
Like how, like, which of the.
can. Is it increasing here?
Oh, it's decreasing.
Yeah. Here? Here? Yeah. It means as you go from left to right. Yeah, I should have probably pointed that out. So it's increasing from here to here. So they're asking over what domain is it increasing when they say
So increasing
So-
X.
But when I say bar, don't we have to do both?
Yeah, so for increasing there's only one answer, this yellow one, but for decreasing there's two answers, two parts. Yeah, so it's a bit of messing around. It's good practice, in a way calculus is good because it practices your functions like this.
This is calculus. Oh, yeah, really.
So increasing, notice it's from 1 to 5. This is still calculus, it's graphs of derivatives. So that's how you could write an answer. So see how you can write it like a domain?
Yeah.
Isn't it equal to 1?
That's a good point. Remember the gradient at the maximum and
Zero.
min is 0. So it's not,
So
not
we can't
increasing or
account it
decreasing
money.
at that point. It's in the point of changing from increasing to decreasing. So it's at a point where it's changing from negative to positive. So we don't include, that's a very good question, we don't include those points. So maybe let's do all the increasing ones to start with, and then afterwards we'll do all the decreasing ones, which is the best way to do it like that. So decreasing. Is anyone, do you want to do all the increasings first, or
We should do one of what?
let's just do one at a time? Okay. So decreasing. Well, how would you describe that interval? This first interval on this first one. Yeah, from negative infinity to
Positive infinity.
to 1. Yeah, that's one way of writing it. Yep. Or you could just say x values less than 1 as well.
Yeah,
X is less than 1. Yeah. So you might find in the book they might use negative infinity. a bit, So I'll write that just so you get used to it. Okay, so I'll write it like that, but you can write x is less than 1. So, but I've noticed sometimes in the book they'll do this. Negative infinity up to, what's it? 1. Right. So from negative infinity to 1, there's also another decreasing part.
I don't see that far.
Yeah. Good. Yep, sure thing. Yeah, so good. Like you're realizing to use the x's and not the y's. Good. Yep. So also from 5
If you want to fill up a water bottle, you can.
to positive infinity is a way. Quite often you'll see it in the book written like that. Just so you're aware of that notation. Katie. Katie. Katie.
Just go. I'm confused.
Katie. Is it increasing or decreasing? Okay. Krista. Is
Yeah.
it increasing
Yeah,
or
sorry.
decreasing here?
Increasing or decreasing here?
Yeah, here. Decreasing. Let's go from left to right.
Increasing.
Increasing. And Calvina. From here to here.
That's actually like Calvina. Yeah. Is it increasing?
Yeah, it's increasing. Good. What's this funny little point here, do you think?
Point of in.
Point of inflection.
Go
yeah.
Asia pal.
So at point of inflection, it's neither increasing or decreasing. So that's a POI.
Just
Point of
reflecting.
inflection. That's right. Because I couldn't be bothered writing point of inflection. You can write point of inflection if you want. So there's actually 2 periods where it's decreasing.
It's when they
There's the lefty bit and the righty bit. So just to point out, there's 2 separate intervals. Because here, at the point of inflection, it's neither increasing or decreasing. It's going back to the 0 gradient. See if the tangent would be horizontal. So there's just 2 separate periods where it's increasing. It's never decreasing. It's just increasing.
So it's probably, they'll always have the arrows.
in this room.
Nah, but you could assume there's arrows on the end sometimes.
So are they both?
Oh, you mean these arrows?
Yeah.
In these ones, I do, I guess.
But like, how would you tell if it's decreasing if they don't have the arrows?
Because it goes down that way, left to right.
Oh, yeah, it's the rules are from left to right as you go from left to right. So if this was a hill, if this was a road, are you driving up it or down it? As you
You're
go from
driving
left to
up it
right.
all the time.
Yeah, except for there, you're on a flat road at that point. At
But
that very
then why
small
does the
point.
You should demonstrate the road.
These arrows are just to point out that they go on that way. So that's a good point. Yeah, the arrows aren't to do with the direction. It's just to show that it increases. It doesn't stop at those points. So these arrows on the end are just to point out that the graph doesn't end there, it goes on. So Katie, how would you describe this interval from negative infinity to 0? Yes. So it's increasing from negative infinity to 0. And Felix, how would you describe this green increasing interval? Yeah, exactly. It is just as simple as that, yeah. 0 up to positive infinity. That's negative infinity, you'll think it's going to be funny. There's no decreasing point. But rather than just say from negative infinity to positive infinity, the point of inflection has to stop us from doing that. Because it's increasing, then it's flat for a second, and then it's increasing again.
You have 6 minutes left.
Oh, gosh. Alright, this one's got some increasing bits, and then how many decreasing bits? 2. Yeah, so we've got 4 things to write up. What would you write up for this one? Yeah, you tell me. No?
Negative infinity is x and
0, yeah. So that helps you to forward heading to 0.
What's on basement of voice?
And the other increasing you did?
6, 3.
Good, yeah. So notice Sarah's focusing on, she's making sure to pay attention only to the x's because that's what it's asking. It's not asking for ranges when it's asking for these intervals. It's asking for what are the domains when it's increasing or decreasing. Anyone want to suggest?
Yes, I will.
Increasing one?
okay, about 6.
0 and negative 2.
6 to positive infinity, and yep, and 0 to? Right. Yeah, they can be little sneaky ones in there.
6 from.
Yeah, from here. Yeah,
I figured out.
Why do you have to be that way?
It's a positive infinity. So that's part of the decreasing interval. And then the last one.
We have stuff.
See, what are these funny little dodgy things called? Asymptote, yeah.
Go back to the example.
Yeah, that's what calculus is good. It realises these functions a lot. So we've got 2 sets of asymptotes. One at x equals 4.
And y.
Bella, be quiet.
Oh yeah, you're right.
And
There's
y.
also there is one at y equals 0. Yeah.
Oh,
Yeah.
that one.
Yeah, there's a horizontal one too.
X equals 4, x equals 0.
Yeah, they're our little, but they're because we're talking about domains, kind of like
That's all that
x
matters.
intervals. Yeah, but I'm only worried about the x one. So, on this arm, we call this one a little arm. The one on the left is it increasing or decreasing?
Yeah, that's decreasing.
So how would you describe that interval in terms of x? It's from
Negative infinity.
yeah.
And 0.
Yeah. To 0. So seeing negative infinity to
So how would we,
Repetition.
how would we zero if it don't really talk?
That's why you don't put the
that's
line.
right. That's why I opened it equal to.
So you want to put that on these ones?
Yeah, on all of them notice we tend to not put the equal sign. Because at the maximum it's not increasing anymore, it's just hit the flat. It's horizontal suddenly. Because when it's increasing and then it's horizontal. Like then it's on a flat road. A hot second. It's also decreasing, would you say, from here to here? So how would you describe that one?
0 and 2.
0 to 2. So now we're just going to talk about the increasing bits. Katie, what would be the interval for it's increasing from here to here? 2 to 4, yeah. 2 to 4 doesn't include 4 because that's an asymptote. And the last one, Sarah, is within 4. You might find in the textbook sometimes there's other ways you can do these if you're ever in a real rush. If it's not including, you can put it in brackets like that to 0. And if it was including, you would put a square bracket. That's a quick way of saying, but because they're both not including, you can kind of do it like that. That's another notation for writing like this. And if it did have an equal to sign on it, you would just have a square bracket.
Okay, let's just
Just on the end or on both sides?
On the bit that would have the equal to. So if both of those were equal to, you'd have square brackets on both sides, yeah. Because the textbook does that too. That's another way of writing a domain if you're in a rush. You can write it like this. The next parts are a bit hard, so I might quickly rush to Page 27. The next ones are a little bit grueling and they go on. It's a long example. So let's maybe just go up to the last page. I think
We have
it's
2 minutes
27.
left.
Yeah, see, we could do, oh, not that one. We've used that one already. 27, page 27 we could do in 2 minutes. And then the ones in between we can go back to when you come back.
Oh, you mean like in September?
Yeah, I know. Isn't that weird?
Oh, at least I yeah, no, I was like, yeah, we're not going back to class.
Yeah, I mean, like, it's just going to feel weird coming back then. But this is nice. This is kind of a bit more recap too. Yeah, good, exactly. So we already realized, for example,
Linear.
if the function is quartic, the first derivative will be a
Cubic. Four? Just look to me, it's a four.
quartic power of 4, x to the power of 4.
So,
Like the highest power of x is a 4.
oh,
A
the
quintic,
derivative will be a cubic.
yeah, exactly, yes. A quintic would be x to the power of 5.
Yeah.
So for example, if it's a quartic, the first derivative will be a cubic, the second would be a
Quadratic. You think quadratic will be x to the 4, wouldn't you, pal?
an x squared. The third derivative would be a linear.
And then the well, something would be a
And then the fourth derivative.
coefficient.
That's fours.
Oh yeah, what's it called?
This is two.
Do you remember what it's called when it's like a flat function? Constant, yeah. Constant function.
I got an interesting because I said try.
Would be a constant function.
But I'm
So just this is just kind of pointing that out in graphy form. So little examples, and then we'll finish off with these. For the following graphs, imagine these are the first derivative. So imagine both of these were f dash x. So we could label the axis, the y-axis f dash x. Because I've called them not the original function, but I called them the first derivative. Just for the sake. What kind of graph is the first one, Kate? Like the general kind of graph. Quadratic, yeah.
Come on, go Catherine.
Calpino. Or does anyone, you might not be aware of these ones, but what kind of graph do you think?
I was just like using.
Is it not a cosine?
Close, it starts with C. The cubic. Notice that a
But
quadratic,
that means that it would be four, the third.
No, it's not. That's the pressure, but then the second one, there will be linear, and then that one will be quadratic.
yeah, each one goes down by a power, by an exponent, yeah.
You got the graph.
Yeah. So you probably weren't sure where this was going, kind of thing. Yeah. So imagine the question is just pointing out that these are the first derivatives, and the thing you're asked to then is have a vague sketch of the second derivatives. Was that to say something? Notice that the reason why you can also notice that it's a cubic is notice that a quadratic, what's the highest power of x in a quadratic?
2.
2. How many turning points does it have?
One.
1. Yep. What's
So
the
it's
highest?
I
Yeah.
see
Yeah,
it.
what's the highest power of x in a
3.
cubic? 3. And how many turning points can it have?
2.
Yeah.
That's pretty
A cubic
awesome.
can also have just a point of inflection as well, but it's possible for it to have 2. So a quartic could have how many turning points? Quartic could have 3 turning points. Yeah, a quintic could have how many turning points? 4, yeah. So that's kind of a helpful thing as well. Okay, sketch the second derivatives. First of all, let's just kind of plan what kind of graph would it be.
Linear.
This one's going to be a linear, yep.
Second one quadratic.
And the second one will be a quadratic, you're right.
Yes.
Hey, I'm trying to.
We are multitasking, so we guessed it before she even said it.
No, you didn't.
Yeah, we started.
So what can we label the y-axis?
Y and X.
Yeah, f dash dash x, because it's the second derivative this time. F dash dash x. Yay. Now, what's interesting is the coordinates of the turning point. What's the value of the gradient at the turning point?
0.
0, yeah. So notice that it's got to cut the x-axis at that exact point. So what?
It does.
Yeah, what is that point on yours? I can't see.
-2.
Negative 2. So at negative 2 is where it's got to cut the x-axis. So negative 2, because that's where the gradient, because notice this is the gradient of that. So the gradient is 0 at that turning point. Where is the gradient? To the left of it, is the gradient negative or positive?
Positive.
Yeah, it's positive, so it's got to be up above in the positives. Isn't what it has to be positive? It is. And after the turning point, what happens to the gradient?
Negative.
It's negative, so it's got to be down in the negative.
Oh, this is linear.
Yeah, because it's a linear one, yeah. So,
So you do it according to the turning points, isn't it?
yeah, exactly. The turning points kind of like help to account for the x-axis. So if you want the blue bit, it's that, and then continues down here. It doesn't matter, like vaguely. That's meant to be just one line, by the way.
I want to cry. I'm trying to do it with another one line. I thought I did so bad in business.
Okay. So that makes sense, yeah, at negative 2. So, because that's at negative 2. So that was an important point. We know that the derivative of the second one, the second derivative, has to be a quadratic. Because
the cubic is big.
Good, yeah, well done. And so, what will the two turning points tell us about the graph of the
Once you go positive, once you go negative.
yeah, the x-intercepts, yeah. Because remember at the maximums and the minimums, the gradient's 0. So these two things are going to tell us where the what are they called? X-intercepts are. So notice the x-intercept is meant to be slightly to the right. It's not exactly on the y-axis, that one.
The x-intercept?
Yeah. So I've tried to make it. I've tried to make it so these things line up. So these things line up. So your x-intercept, your x-intercept's going to have to be line up with that. So at about here, like wherever that point is on yours, the x-intercept for this one's going to have to line up. So about here. That's what I do first, is I identify where my x-intercepts are, because that's where the gradient's negative. At the beginning,
This for learning?
yeah, keep going.
Wait, but isn't it 3 axes in there? No, but I'm
But I
saying
see
that.
3 x-intercepts.
But
On
I'm
the original.
Oh, we're talking about China's place. Yeah.
Yeah, that's right. Yeah, the turning point is to identify the x-intercepts on the next derivative. So, Bella, would you say the gradient at the beginning, is it positive or negative? So it means that, would you agree that it means that it has to be above the x-axis?
Wait. Okay, yeah.
And from here to here, between the two x-intercepts, is the gradient negative or positive?
Negative.
Yeah, so that's why they have to be below.
This is so wicked.
Because this is saying what's the gradient, yeah. And this one's positive, so from here it's got to be above.
This is wicked, isn't it?
Isn't it weird? Just sort of thinking how you can kind of graph and visualize the graphs of the derivatives. So you might want to make little extra notes of why we did this one above the x-axis.
I don't know how to word that thing.
It's hard, isn't it?
Everything increasing and make it positive.
It's okay.
And make it negative.
Look at it, I know.
Alright.
Usually I write those like something out of right now.
Okay, last one. Switch the third derivatives. Let's do it fast.
It's
Third
not
derivative,
negative.
f dash x. Yeah. And remember, once we get to the fourth derivative, we just write f4x. Yeah. The third one we've done.
So this is going to be a constant.
Yeah, this one's going to be a constant.
And this is going to be a linear.
Now, what's interesting is the blue line above. Is that got a negative or a positive gradient? Negative. So it's got to be a constant, and it's got to be below the x-axis. Because it's got to have a negative. Yeah, just anywhere below the x-axis.
Anywhere,
Yeah.
anywhere.
And that one goes this way.
Yeah, that way. You were wrong with that. That way.
Oh yeah, where's the turning point? I've done in a really dodgy spot.
Because the top part is decreasing, so you have to start from underneath.
Yeah, you're right.
You're cool.
Oh, noticing it's below the x-axis.
Right, but because the intercept is negative 2, we have to get negative.
Oh yeah, good point. Yeah.
Okay.
I think so. It's more to do with the rise. It's more to do with the rise over the run. So don't quote me on
But
that.
it would
So it wouldn't be negative 2. It could be.
I think the main thing is it's just got. So now let's just
Okay.
say it's got to be negative. So it'll be in the negative because it's a negative gradient. Let's not quote me on that. The next one we already know it's going to be linear. The turning point should match up. I did a really bad turning point on mine. Just make sure your turning point matches up with the correct spot. So here's the turning point. So it's probably going to be more like down here really. It probably should have been there. And Keisha was pointing out that to the left of the turning point, it's a negative gradient. So it's got to be below the x-axis.
That's a nice quadratic graph.
So it's got to be going up like that. And to the right of the turning point, but your quadratic graph looks a lot better than mine.
I'm sorry, why is it there, Mr.
That's what it's pointing at.
Negative gradient.
Yeah.
So below the x-axis.
And positive gradient.
A positive gradient, so it's like above the x-axis.
Okay, we're done.
And the very last thing, what kind of graph would have been the original function? If this, if
That's wrong. We have 2.
Yeah, you're right. Good. How did you get cubic for the first one?
Make a what one?
Oh, that's 1.
Yeah, because the first derivative was quadratic, so it meant the original must have been a cubic.
Would it be higher?
It's got to be one higher than a
Oh yeah,
quadrant.
sorry. Okay, gonna make it as 4.
And the original for the other was a cubic. So what's it for this one?
Well
And
done.
you don't have to sketch those. When we do integral calculus, you might be asked to sketch those functions, but we haven't done integral calculus yet.
You talking about the flat land here?
Yeah.
Okay.